Hello, hello.
Speaker is here.
Hi. Hi. Nice to meet you. Hi. How are you?
Good. You're the first.
Yeah, I'm the first speaker.
He was afraid that he has to give a talk to himself. But hey, hi.
It was very interesting.
See?
I looked at your title.
Oh,
It's very interesting.
I hope I don't disappoint you.
People talking now departments. I have a lot of seminars, colloquies.
Yeah.
Very interesting.
I'm trying to finish this thing. Probably I'll finish this and I'll give a talk on that. Yeah.
Remember, we have interacted with email for some time.
Yeah, when I applied long back.
Yeah. That time, physics is.
Good morning, everyone. Welcome to the day 2 of Chennai Stock Market Days, and the first presentation is going to be by Ganga Prasad, who is faculty at the Department of Applied Mechanics and Biomedical Engineering. They changed the name very recently, right? That's yeah. And he's going to talk to us about behavior priors for control of collectives. Yeah, thanks. 35 minutes, I'll just give you a warning, or
Sure.
30 minutes, what do you want?
Yeah, 35 is good. Yeah. Yeah. Thank you very much, Professor Basa, and thanks to the organizer for giving me this opportunity. This is my first time in IMSC, and it's actually a really nice campus, and I hope to come here more often. So I'm a new faculty in the Department of Applied Mechanics and Biomedical Engineering, and it's essentially an engineering department. So we have a new lab. It's called an interface. It's called the Interface Lab, and sort of the broad agenda is to use ideas from physics and biology and use it in problems in mechanics and robotics, so that you can use them in productive ways. So the talk that I'm going to talk about today is part my postdoc work, and then something that I've been doing for a while, and it's been in the back burner since the semester started. It's called behavioral priors for control of collectives. It's little grandiose in its mission, but at least I'll try to convince you that there is some progress that we can make if you take biology as inspiration. So the broad outline of the talk is we're going to talk about this notion of sociality, which is essentially there in animal kingdom, and then we're going to use social insects as our model system and be inspired by them to create artificial agents or robots that can perform some collective task. And I'm going to talk about some new work that I've been working on navigation, again inspired by social insects, and some room for progress in theories, which I think I would require a lot of input from people here on adaptation, and I'll just leave with some conclusions. Okay, so the big picture is that the animal kingdom is stratified into so many different ways, and one of the ways where you can actually ramify them is this notion of sociality, where animals are either solitary, social, or eusocial. So solitary animals are ones which are basically by themselves for the most part, except for courtship and mating. Some of the examples include snow leopard, polar bear, turtles. And the second way by which you can classify them is the social group, which is the biggest group. You have crustaceans, you have scorpions, moths, beetles, spiders. They are all social. They are not really living by themselves. They share space with others, others of the same species, and they interact with each other primarily to share resource. And the top, and there's of course further stratifications that are possible, which I'm not going to discuss here. And the higher up in the hierarchy is the eusocial set of animals or insects for the most part, where these groups, this set of species can actually perform cooperative tasks. They can take care of themselves. They have cooperative brood care. And strangely enough, most of the colony of these insects are sterile. They cannot reproduce, and they essentially have reproductive or dominant hierarchy. There's usually one or few reproducing queens for the most part, and they have overlapping generations. So they are all sisters by genetics, and they actually take care of themselves. And they can perform a whole lot of tasks together. And the most common examples are termites, ants, bees, and wasps. So I'm just trying to motivate why social insects are interesting, both from a biological standpoint and a physical standpoint. The first point is that these insects can actually perform a variety of tasks. Some of them are, they can forage together, they can perform tasks like nest maintenance, they can perform brood care as I mentioned, they can do construction and repair, and they can also defend themselves against various kinds of predators. Why is this interesting from a physical standpoint? The reason it's interesting is because these agents are all completely autonomous. There is no central control. So essentially these are independent agents making real-time decisions, and all the tasks that they are performing are performed without a map, which is to say any task that I highlighted earlier is performed by these agents just in real time without them actually knowing what is the bigger picture of their actions. So in that sense, the task itself is emergent. So if you take a single ant, for example, and then just track its behavior, you wouldn't be able to predict what the macroscopic task that they're performing is, and which is fundamentally very similar to sort of the emergent phenomena that we are used to in physics. And the other interesting aspect is these agents are all adaptable in the sense you tune or change the conditions of the environment. The task itself seems to be robust to perturbations in the environment, in the sense that they're able to actually modulate their motor actions such that the task is still successful. So then the question really is going back to, can one learn from these social insects to design better artificial systems? So that's sort of the broad goal for now, and we're going to take ants as our specific model organism and try to see if we can build systems inspired by these ants. So just a couple of minutes on ant morphology and physiology. So ants essentially have, so their afferent system, or essentially the sensory modalities, are pretty complex. I'm going to stick to very shallow description here. So they have, their body can be divided into head, mesosoma and gaster. So they have eyes with which obviously they see, and they can also see well into the UV spectrum, and they have mandibles with which they can modify their environment, manipulate their environment, and they have antennae with which they interact with each other, and they can also sense pheromones, and they have legs with which they move, and the gaster part is where the pheromone organs are located, and that's what they use to lay the pheromones. And there is this thing called the ocelli, which is actually not completely well understood, but it's supposed to detect light intensity. So that's sort of the broad physiology, and with which they actually have a set of, so this is sort of the physiology, and they actually use this physiology in order to perform specific set of motor actions which are called behaviors. And here is one very famous one which I'm sure you've all heard of. It's essentially trail following behavior. So here is the trail of pheromone which an ant is able to track quite well. And this study, this paper that came out a few years back, was looking at how they, what's the strategy of antennation they use in order to ensure that they don't go out of track. So essentially they use their antennae to follow pheromones, and they do it really, really well. And they also have sensory organs in their mandibles that can detect forces acting on the objects that they are carrying. So even though in this example you might have seen there is a leader who actually helps this collective to drive this entire food towards a particular direction, and they are not communicating via some external means, but they are using the object itself to transmit information. So there's again some sensory feedback coming from the mandibles. And the last thing that I want to show is they also use tactile feedback, essentially by touching each other in order to determine what to do next. So here is a set of collective of ant, and here is the sort of the contact map, if you will. So all these points are where all ants have actually made contact with each other, and you see that this contact network is pretty dense. That's just tracking. They're just tracking the, you see the body axis angle that's been plotted. It's essentially just the orientation of this line. And it's all imaged in the dark. So there's also cruel process by which they've extracted the pheromone and they've laid it out, and then these guys are walking on this trail, and it's imaged in the dark. Yeah. Okay, so the broad understanding as it stands today is that of embodiment, which is that an agent's behavior is determined by firstly other agents, other ants, and it's via their communication through antennation or pheromone, and it's also modulated through the environment. So you have the dynamics of the agent, their interaction, and then the environment in which they live, which determines what they actually do. So with this sort of broad outline, can we go and basically design artificial systems that can perform some of these tasks that these agents can do, these ants can do. And the specific task that I'll be describing today is that of construction, and I'll just briefly show some earlier results on deconstruction that again I did during my postdoc. So we are going to use for this bottom-up approach, just like I've described today. We are going to build these agents which have similar morphological capacity to that of an ant. So this is the sort of the custom robot that we built in our lab. They have essentially haptotactic and phototactic feedback, which is to say they can sense if there is something in the front or not through these bump sensors, and they also have phototactic feedback. They can detect light. They have two light sensors at the bottom with which they can detect if any light is projected at the bottom or not. So that's, I just want you to keep that in the back of your mind, because that's going to be useful for what we look at next. And it has a microcontroller, sort of the brain, and it has a servo motor with which it can pick and drop objects, trying to mimic mandibles, and it's powered by motors that power wheels. So these are wheeled robots. Yeah, so the capacity of this agent is sort of similar to that of an ant. So it can manipulate the environment via these servos with which they pick and drop objects, and they can sense if someone is in the front or not, and they can also sense light field at the bottom. So this is approximately 5 by 5 by 5 centimeter cube. It's, yeah, this is all the components are, off the shelf, and we were trying to do everything in house, but this is essentially put together in the lab. Yeah, I mean, after this is the 5th generation, and then the setup itself is as follows. I'll just describe briefly how this idea of mimicking pheromones works. So this is the experimental setup where we have a table and we have a projector at the bottom, and there is a camera at the top that tracks where each robot is on the table. And then this projector will essentially project light onto some translucent sheet, and by tracking the location of each robot, we know where it is, and then you can essentially project a light field that mimics pheromones. So is that clear? So the idea is you track the location of the robot, and then you can project a light field along the trajectory that each robot actually travels. That's the only reason why reason we actually build something outside of just the agents. You can imagine this is a setup that just mimics pheromones, where this robot is able to just lay light field. Okay, so that's, and we call this photomone because it's generating sort of photons through this projector. Is this clear? So, and then the environment itself is just set of PVC pipes with magnetic rings, so that these robots can just pick and place those PVC pipes. Okay, and so we essentially have also the components required for this embodiment, which is the agents. They're communicating with each other via this photomone field that they're going to generate, and the environment is essentially here the substrate. Okay, so as I mentioned, we're going to use the bottom-up approach. So let me briefly describe what the dynamics of a single agent is. So the dynamics is given by this. So each RANT can, so we call it RANT, robotic ant. We were just too dull. Yeah, it's a dull sounding name, less creative. Yeah, so the position is going to evolve as V0 times P hat, where P hat is the orientation vector, and the orientation dynamics is given by some rotation velocity, and then the rotation velocity is proportional to the gradient in the field that it detects. This reduces to chemotaxis framework. if you just assume small angular deformations. And this is essentially the dynamics. And let's see what happens to this dynamics when you assume that there is a background field of light which is having a constant gradient. So the gradient is just decaying as a function of distance from a given center, and in that limit you can actually write this dynamics into this set of phase which is given by the angle made by this orientation with respect to the global reference frame, and then the distance from the center itself. So essentially this dynamics reduces to this, and you can immediately see that there are two fixed points in this dynamics which is given by these two values, where psi star is pi by 2 and r star is v0 by g lambda. Just a quick reminder, g is essentially the gain, which is telling you how much I turn when I detect a gradient field, right? So that's the proportionality constant, or you can imagine this as the chemotaxis strength. So this is the fixed point that we get, and you can see that this fixed point corresponds to a circular trajectory. So this guy is just going to keep revolving around this constant gradient field at a particular distance away from the center. And we did these experiments, I'm just showing you a sample. This is from the robots that we built, and you can see that it follows nicely this result that we found. This is just G is something we can control, yeah. So next we went on to see what's the dynamics when these agents can generate this photomone field, which is given by this simple rate equation type equation, but just that it's now spatially dependent field. So this is the evolution of the light field itself, where it's being generated by the agents based on where they are, and there's a constant decay rate to this intensity field. This is just the density field, and it can generate this field with a given width W. So what we again found was there's a obviously when you do these experiments you have to account for all kinds of finite size effects. So we found that actually the distance between the sensors start playing a role, and you can find essentially a similar trapped phase for these agents, and that's determined by the width of the ratio of the width of the light field that's being generated and the distance between the center and the gain. So there's a critical gain for a given width of light field that's being generated at which these agents are going to be trapped. And again you can do these in simulations, and then this one. This is just generation of. Yeah, so if you imagine we are trying to emulate pheromones, so pheromones are going to just decay after a while. I mean, essentially they are volatile, they can diffuse, and they can also, we actually assume both diffusion and decay, but I'm just showing you this with decay. So there's a length scale associated with the speed and the rate of decay, which is sort of, I think this might be there in the schematic, yeah, which is basically this length scale. That L minus is telling you the length scale over which a given concentration field is going to survive given there's V0 velocity. Yeah, so this is the trap, we found that these guys are going to get trapped, and we can calculate this phase boundary both for single agent and also for several of them together. And so from here on, our ultimate goal was, okay, so now we have this dynamics, how do we make these guys essentially perform this task of construction? And what we had to do was cook up a list of behavioral rules associated with when to pick up and when to drop. I've just listed them down here, but the way we came up with had some biological inspiration, which I'm not going to talk about today. But the rules that we came up with are to follow gradients, just like what we've seen in the passive dynamics, and pick up objects when the intensity of light field is small, and drop them when it crosses a critical threshold. And on the way back, just avoid anything, just avoid obstacles and other robots. So these bump sensors actually cannot distinguish between other agents and the boundary element itself. So it's sort of agnostic to that. So even with this very simplistic set of rules, actually we got something very interesting. And this is what we got. So let me just play the video and then explain. So what happens is, this is the full experimental setup. So you have these PVC pipes and we've just marked them so that we can track these guys using the camera recording. And you'll see hands of mine and Fabio, another postdoc in the group. We did this together. And so what we see is that they actually use this trapping instability to create the nucleation site. And then use this nucleation site as a way to actually start putting in these elements at that given location. So you see hands because we didn't have enough elements and our domain was small. So, and as every time they visit that site, they spend more time and that light field gets reinforced and this process just continues. So essentially the trapping instability is used to create this nucleation site which can then be used as a site for construction. And this came about like in speaking to the broader goal of using behavioral priors for a specific function seems to work here in this case. And then now you can tune parameters in the experimental setup and then essentially get some heuristics. So here is the area of the cluster as a function of the cooperation parameter, which is how justly they follow the pheromone trail. We see that with increase in cooperation, and this is averaged across several trials, is that the cluster size increases and then they are also more compact. So the perimeter of the cluster itself goes down with increase in cooperation. And we also found, as I mentioned, there is this threshold beyond which these guys start this construction itself. We went and checked how robust is this essentially strategy by closing down the, like cancelling the threshold and also playing with the cooperation parameter. What we found was both of them are really important if you want to get successful construction. So you have to be really good at following pheromone trails and there is some collective threshold that each one has if you want to get a successful construction. And this actually also generalizes to this task of deconstruction. I'll just show the video here and then I'll leave it. I can discuss more about this if there's interest after the talk. So essentially the same setup, we showed that agents can perform construction and escape or deconstruction without again a map of the task. And what you'll see is that these guys are, this is the background light field that it's self-generated and they use that to start escape and they all leave the boundary. So again you can calculate how well is the escape based on the time it takes to escape and also the variance of the tunnel that they may make. And it seems to, obviously with cooperation, this efficacy is improved and that's just an observation. So with that, that's essentially part of my postdoc work and then navigation is something that I'm working on right now. Yeah, I think I'll spend the next 15 minutes talking about that. So navigation, just like construction, is really a fundamental task that each colony has to do so that they can go and forage for food. So navigation itself has a variety of strategies and there's a hierarchy in the animal kingdom. The simplest one is what is known as locomotor guidance, which is essentially just following trails laid out by someone else, and it's also egocentric. So egocentric locomotor guidance strategies are primitive and they are much more simpler to implement and you don't need a complex neural background to essentially implement this strategy. And the second strategy or slightly complex strategy is what is known as path integration, which I'll describe briefly. And for you to actually be able to do path integration, you also need a physiological basis. I'll briefly describe that as well. And then the third complex strategy is essentially landmark based navigation, where you're able to place yourself in the context of your environment. So you move from egocentric, where you just have a representation with respect to yourself, to a representation set in an environment. So that's the allocentric framework, where you now have an understanding of the environment and you place yourself based on that, and that's the landmark based navigation. And the most complex that humans and I think mice and other complex animals use is what is known as map based navigation or route based navigation, and that's the ultimate sort of way by which we navigate, because we have an entire representation of the map in our mind or brain. So we are going to stick to path integration and locomotor guidance because that's what ants use, and the path integration idea itself has a pretty fascinating story going back to the early 1900s. So there is a very special species of ant called the Saharan desert ant, Cataglyphis, which exists and which does foraging in the desert where the temperatures can go up to 70 degrees Celsius. So at 70 degree, pheromones being volatile will just vanish really fast, so they have to actually come up with a different strategy to ensure that they can convey this information to other agents, and also to be able to go back to the nest so that they're not lost, because you cannot use landmarks. In desert, there's everything is the same everywhere, it's isotropic. So what they found was, this is an experimental trial, and the initial observations were made by this Swiss and Italian, essentially engineer and a librarian who were posted in Africa, and they found these ants roaming around, and they made some interesting observations about them. So this is the trajectory of one Cataglyphis, where you start with its location in the nest, and then they go on this outbound trajectory along this trail, and then they find the food source, and then what they found was these guys essentially just walk back to the nest. So this is the outbound trajectory and this is the inbound trajectory, and along one direction it seems to take a much more roundabout path, and on the way back it seems to have a much straighter path. So this was really perplexing, because the size of an ant is like 7 mm or let's say 1 centimeter, whereas the size of this trail is 1.5 kilometers. And this guy is able to do this, and this led to several sets of experiments, and Wiener in the early 2000s came up with a very, very nice set of experiments to understand how they do it. So what Wiener did was, in this really nice paper, I think he's written a series of really, really nice papers, where he hypothesizes that the ant needs to have two things. One is a pedometer or step counter, odometer, and also a way to measure angular velocity or angle differences. With those two essentially sensory modalities, they can actually integrate that to keep track of what is known as the homing vector. So they keep integrating the past, distance, and the orientation along a particular direction, so that they can keep track of where their home is. And this was before, actually this was, the earlier experiments were before they understood that ants also use polarization in the sky. But essentially it's a combination of this internal step counter, angular velocity measuring modality, which is through this thing called optic flow, and then a global reference that's there in the sky. So it uses these three different information to keep track of the homing vector. So the question that I'm interested in is to see, so I should mention that after they did these experiments with ants, it's sort of now assumed that all ants have at least a primitive version of these ability to keep track of their home, and also to use the global reference, which is the polarization in the sky, to keep track of home. So then with that context, so the question that I'm right now interested in is, how would ants be able to navigate in environments where you already have a pheromone trail? So let's say you already have a pheromone trail, and that pheromone trail is leading you to food source, but now let's say that food source is not sufficient to meet the demands of the nest. At what point along this trail would you have to innovate so that you can meet the demands of the nest? So the approach that I'm going to use to solve this problem is that of reinforcement learning. I'll just describe this real quick. So reinforcement learning essentially is a technique where each agent is described by its state and actions. So agent is, let's say, at a given state, it can perform a particular action and move to a new state, and for performing that action it gets a reward R1, and then it keeps doing this, let's say, till the time step goes from 0 to t. So there are two things that you have to know to sort of understand how reinforcement learning works. One is known as the policy, which is essentially a probability distribution of taking a particular action given that you are at a given state S. And the second thing is the value function, which is an estimate of how much reward you're going to get given that, let's say, you are at state S1. So value function is telling you what is the integral of the reward. Let's say I start from S1 till ST. It's going to sum up all the rewards that I get in all these steps, and there is gamma, just a discount factor depending on how much you are willing to bet on the future. And you can write this value function by expanding this estimation, and this is known as the Bellman equation. And the way you actually solve this Bellman equation is there's like a whole host of techniques to solve this optimization problem. The way you do this is, the simplest way you do this is using this technique called temporal difference learning, where you just take one step and then update your value function based on how much reward you got in that step, given that you're following some random policy, and then you keep updating the policy and also the value function. And there's an error associated with it, which is known as the temporal difference error, and you can keep doing this so that you minimize this temporal difference error and you reach what is known as the optimal value function, at which you have a set of actions that you have to take so that you can perform this task in the best possible manner. So that's broadly the technique of reinforcement learning, and this temporal difference learning itself has some recent research in neuroscience, and where they found that we are also probably using something like a temporal difference learning to learn our tasks on a day-to-day basis. And there is some connection to stochastic optimal control, which I think I'm going to skip. And this is the exact problem that I'm looking at. So let's say you have a given trail which is in this semicircular manner, and you have your home or the nest which is at B and the food source is at A. And you have already traversed this trail, and you have some vague idea of where the food source is, and now you're not able to meet the demands at B, and you have to start innovating from the semicircular trail so that you can reach this food source in a fast manner. An important thing to note is that your state space and then the action space is actually right now continuous. So your state is given by the position, and the action is essentially the orientation. Both of them are continuous, and it's often very difficult to perform these optimizations on continuous domains, which is where the behavioral priors can help, and it actually reduces the complexity by a lot. So the way we do this is essentially split this problem into two parts, where you're able to follow the trail up to a given location, and then after a point you start doing this exploration, and you assume a policy or essentially a process by which you perform this exploration, and you have also a reward that is a function of where you leave the trail. So if you start leaving the trail much earlier than, let's say, the food source, there's going to be larger error, and that's captured through this OU policy, which I'll show in the next slide. The diffusion is going to be much larger for, let's say, breaking off at this location than at some other location. But of course, if you break off here and hit this location, then the reward is also going to be larger. So there is essentially something like a speed accuracy trade-off, but now in the spatial domain. And it has this problem itself has some connection which people have studied in minimum variance in motor tasks and things like that. So this is how the passive dynamics without learning happens. It's just an agent just following this semicircular trail, and then it breaks off and it accumulates some reward along its trail. And if you do learning on this, this is how it works. So these are several trajectories of this agent, and then this is the reward that it gets. And using TD learning, you can see that you can parameterize this entire value function just along this arc length or just the angle, they're both the same. And you see that you arrive at a policy. Once you have actually found out the value function, optimal value function, your policy is just going to be just pick the angle with maximum value, and you're just going to walk along that direction. And because that's where the probability of hitting the target is maximum, or the variance is going to be minimum. Yeah, so you have, this is the dynamics of the learning itself, and with some very simple calculation, you can actually capture this non-monotonic behavior, which is that, you know, the intrinsic policy is just can be mapped to a worm-like chain model, for which you can exactly evaluate the value function. So I'll be done in 1 minute. And then for the Ornstein-Uhlenbeck process in the orientation, it's in the small angle limit. This is just going to, the variance can be exactly evaluated, and you can also calculate the value function exactly, and you can calculate the total reward. So you can put these together, and then this is just some result showing that this is the value function that the agent learns, and this is the prediction from this essentially the model, and they both match well, which is to show that, or the larger point of doing this is that the agent's capacity to keep track of where the final food source is actually limited by how well they remember the food source itself. So let me state that again, say this again. So an individual's capacity to find the best solution is sort of limited by how well they remember their previous trajectories. And if you imagine a collective setting, you can see that you're always going to reach some suboptimal solution, because the shortest path is essentially the straight line, and which if you choose an agent arbitrarily, their capacity is going to be limited such that they can never find that optimal solution. So which means that diversity is sort of important if you want to find better solutions, and that's something that you can infer just by looking at the single agent dynamics. And the thing that I'm right now working on is essentially extending this to many agents. And the really interesting thing, so the usual approach is what is known as central controller approach, which is not something that we are interested in. The ultimate solution that we propose is essentially using pheromone as the reward information itself, which might be something that the agents are using. So if you imagine there are two trajectories, one shorter than the other, and we know that ants actually leave pheromone trails on the way back. So like here, you'll see it finds the food source, and it's not able to carry the food source back. So what it will do is, I'll let the ant do its thing. So it tries to pull the food, and you see the motion is very choppy because it's actually laying the pheromones. And you would also you might also want to remember that the outbound trajectory was different from the inbound. And then with this pheromone, which is encoding the reward, actually it has managed to convey this information about the food source in one go, and which is why it's called one-shot learning. And that's one way by which collectives can learn these tasks, and which is what I'm trying to implement in this problem. And there are, I think, a lot of interesting statistical physics questions associated with this. I'll just leave them here, and I'm happy to talk about it over tea. And yeah, I'll just leave this slide, conclusion slide, which says that it's really important to account for this changes in environment and use the embodiment framework. And our approach is really going to be analysis, hypothesis, and somehow synthesis this in the robotic platform. Yeah. Thanks.
Okay. Yeah. Thank you for a very nice talk. In the interest of time, we can take one question, and then there's, of course, there will be time for discussion over coffee. Anybody has a question?
You had this value function which had a maximum, right? So it essentially tells you that there is a optimal distance from where it has to depart, right?
Correct, correct.
But you don't see this in the multiple agents, right? Because in
Yes, so it's different in the sense that it's not the exact same problem, but I was just trying to say that you can implement this kind of learning in collective. So the way traditional people do it in collectives is you have one, let's say, neural network which is just learning the task. All the agents are essentially just training the same network, which really defeats the purpose of having collectives, right? Because they have their own individual capacity to make decisions. Instead, they use the central network that just takes decisions on everyone's behalf. But one way by which it seems like these ants might be performing this adaptation or learning is by storing this value function itself in the environment, which is through pheromones. Let's say I have one pheromone trail which is weaker than another one. It's more likely that the stronger one has more reward. Like it's probably the shortest route compared to the weaker one. That's what I was trying to say.
Thanks.
While the next speaker sets up, we can have another
Short
question.
quick. Very nice. So my question is something, so you have this small number of robots doing something. How is it an improvement over computer simulation?
Yeah, so
Because
we also did this.
you're actually simulating a model in some sense.
Yeah, we're simulating a model. The really tricky thing, there is this thing called the simulation to reality gap in robotics, where you're not able to account for all the contact forces or the nonlinearities associated with friction, because if you want to capture all the details about the geometry and they're all heterogeneous, they're not identical. So if you want to bring all of that in, you really have to, and if you want to assume that they're sort of subleading order effects, then yeah, that is, you mean in terms of in experiments? Yeah, these are not, yeah, if you design them properly, I think they're scalable. But yeah, I think you need some speciality which I don't have to do them at much bigger scale. Yeah.
I think there's going to be some more time during coffee. You guys can discuss it. Thanks so much. Yeah, the next talk is by Debashish Mandal. He's at IIT Tirupati, and he's going to talk to us about decision making to start or not. Okay, so that's the title of his talk. Yeah. Sorry, to restart or not. That's the.
Sure. Thanks for introduction. Good morning to all. So this is the first time I'm visiting IMSC. So I got another chance when Professor Rajesh invited me to give a lecture. That was just before COVID-19. Probably Professor Rajesh cannot remember that. So what happened? So I applied for a position here. So in end of 2016. So around after 2 years, Professor Rajesh against the same application invited me, but immediately that this COVID-19 started. By the time I was settled down in IIT Tirupati, but it is very nice to come here. And one of my collaborator from whom I actually learned about this stochastic resetting problem, Dr. Arnav Pal is also here. So if anything I cannot explain, so I please refer Dr. Arnav Pal. So today we'll discuss some of our recent developments in our lab, and which is related to a very simple 1D drip diffusion process, which actually leads to a decision making one. And we'll see that in terms of some important quantifier while one decision making process is being considered, that whether we can get benefited or whether we can amplify some of the gain during decision making process using a stochastic resetting. So first let me introduce the model the way we will speak. is a very simple Tom and Jerry game model. So let us consider Jerry is inside a maze, and there are two doors there, and this is Tom and this is some cheese. Right now, first let us consider there is nothing. So in that particular case, the escape of Jerry from any one of the doors, that escape probability is the similar, and depending upon the size of this maze, there will be some characteristic time scale at which it will escape. Now the interesting thing happens if suppose Tom is sitting here and in the other door there is some sort of cheese, then we can consider that if Jerry will obviously always try to escape from Tom, so we can consider there is a wrong decision if Jerry reaches here, and on the other hand, if Jerry can find cheese, that can be considered as a correct decision. Now what we assume that, so in this model we can very simple way we can assume that Jerry can sense some sort of fragrances from cheese, and also some sound or pheromones from Tom can repel him from here. So we can assume there is some sort of drift towards this right decision. So now if we map this problem in 1D, so we can consider that some particle, Brownian type particles are there, and initially and stochastically it is moving, and these are the absorbing boundaries. One of them can be considered as a right decision, another can be considered as a wrong decision. Now depending upon the length scale, and we will have and the strength of the stochasticity, we will have the decision time, and that will give the escape rate, and that can be any one of these, and another will be the escape probability. So either from this window or that window. So depending upon the whether it is epsilon plus or minus, we can say that epsilon plus can be the right decision, and we will find that right accuracy. Now as I mentioned that if there is no bias, if there is no bias in terms of drift nor in the spatial symmetry, so if it is in the right in the middle of the maze, so you can see that the escape probability is 50-50, and there is nothing interesting. But in presence of both Tom and cheese, we can find that there will be a certain drift, and we can find that the outcome, this epsilon plus, will be higher. Physically we can sense that. Now if we consider these two things, that one is the decision time, how long it will take to escape, and another is the escape probability. So that ratio we can define as a reward ratio, and clearly it will be the function of the initial position where it was set and the strength of the drift. Now in decision making process, it is very obvious that something happened, that how to take decision more accurately or quickly, and obviously common sense says that if we can take accurate decision in a shorter time, so therefore we can define that reward ratio as accuracy over time, or in enzymatic kinetics a very popularly known terminology is used, that is speed accuracy trade-off, or SATO, which is essentially the reward ratio. Okay. So now on top of that, if we introduce some sort of resetting, that means Jerry was there, Tom, that window related to where Tom is sitting is a wrong decision, this is a right decision, and we map this problem in 1D. And here, depending upon the strength of the drift and the initial position, there will be the splitting probability, and we will find some sort of reward ratio. Now my point is that while Jerry is randomly moving, if after certain time, if we stochastically reset Jerry in a particular position, initial position x naught, that need not necessarily to be in the middle of that distance. So then what will happen? Whether using this stochastic resetting, we can amplify or we can optimize that reward ratio, or in other words, we can say that speed accuracy trade-off. So that is the issue here. So basically in this context, I want to mention that this problem, although not in the framework of decision making one, was first introduced by Dr. Ornopal, who is sitting here, and in absence of any sort of drift, and he calculated if there is within an interval there are two escape route, and then using stochastic resetting, how we can find that it can accelerate either the escape time, or in sometimes how it will influence the splitting probability. And what they find that depending upon the breaking of the spatial asymmetry, actually they find that resetting can help the escape time under certain condition, and beautifully they have analyzed that thing. So in our particular problem, what we did, actually we just made one simple alteration. We introduced one drift there, and we see the outcome, what is happening. So in terms of physics, it is just addition of this V term with respect to Ordov's paper. Okay. And now, once we introduce that stochastic resetting, then x naught, V and R, so reward ratio will be function of all these three things, and what you will find that tuning these three, we can optimize the Sato. So we want to see this role. Fine. Now, as I am in chemistry department and my training is in physical chemistry, so what is the context in which we consider that? So in enzymatic kinetics, as we all know that there is some beautiful phenomena called kinetic proof dating. So what happens when some enzyme is combined with some substrate, there might be two or multiple similar type of substrate in terms of energy or something, and combination of them will give you energy substrate complex, and essentially you will get some product. Now if we have two similar type of substrate, out of that suppose one is correct substrate, another is wrong substrate, and when enzyme combine with the correct substrate and give the product, so you will get the correct product, otherwise you will get the wrong product. What happened in nature? It has been found that nature has some beautiful mechanism in many this type of enzymatic kinetics, that out of that multiple possibility similar substrate, it always chooses the correct one, and the accuracy in which because it is very high, say for example in some particular DNA replication process, you will find that error is extremely low. And not only that, this phenomena happens in terms of very finite time, or we can rather say very short time. It is not that it takes very long time to find the accurate substrate. So that is the issue, and people, I particularly refer this point. So paper, in this paper, very in simple Michaelis-Menten enzymatic kinetics, it has been demonstrated that how, what are the different kinetic scheme you can explain this phenomena which is called kinetic proof reading. And mostly so far what people did, that people introduces different number of intermediate states where it can to and fro it can go and reach to the product, and also the chemical potential bias. What you can say that energy profile diagram, the multiple intermediate state, and if you break that overall energy barrier into multiple steps, so you can get some benefit from that, and with different mechanism you can find or you can explain the accuracy of this kinetic proof reading mechanism. So what was not considered so far, in fact today we have also not considered till date, that suppose if we keep from any intermediate, suppose this is nth intermediate, from here either it can go to the forward intermediate or it can come back to the backward intermediate. On top of that, if we put another window, that it can come back directly to free enzyme and free substrate. So that unbinding process was not considered yet in enzymatic kinetics, kinetic proof reading processes. So that we can map as some sort of resetting, and we can explain this problem whether we can again amplify or optimize the speed accuracy trade-off by introducing an appropriate unbinding processes there from any intermediate step. So that we can be considered as a context. However, as I mentioned in today's talk, I will only mention that we will only discuss the physics of the problem in a simple 1D model, where we consider this stochastic resetting of the JD's position, and from here you can say that the unbinding processes can be mapped as a stochastic resetting. Okay. So now very briefly, those who has not introduced to the restart problem. So why that resetting problem is very important nowadays. So again I will refer on of this paper. There are some beautiful phenomena and example very in a simple way, where you can find that in physics, chemistry and finances, and even in computer science, there are many phenomena where you can find that actually if we give some restart, that expedites the completion process, that accelerates the completion process. Say for example, if we consider some animal is looking for some food, foraging problem. So in forest it is moving randomly. Now because of the bad weather or the day is over, it is dark, so it is coming back to its home, and next day again it starts the looking for the food. So in between what happened while this restart happened, that food can also may change its location. So therefore it is not necessary that if we introduce some restart or if we stop the search process in between and begins it anew, so it is not necessary that it will delay the completion process. It might actually help also, because in between if this food position location changes and next day morning that animal can get that food very quickly. Similarly, if we consider that finding some optimal solution, if we introduce some algorithm and let us consider the solution is here, and from this point by stochastically moving, if we go to that wrong direction, so it is very difficult to come back and get that particular solution or correct solution. However, if we put a restart here and start afresh, then there is a chance that we can reach there. So in this way, and similar to that you can find in enzymatic kinetics. In this way, the point is that whenever there is some stochastic search process, it is not necessary that if you restart in between that it will delay the completion. Sometimes depending upon some particular situation, it can actually accelerate the completion process also. Now how to understand that when it will accelerate that completion process. So let us first consider a simple system where suppose this ball is rolling down with this ramp to here. So we just assume is as a linear ramp. So there is some drift V and it is coming down. There is no stochasticity, nothing. So in this particular case, depending upon that how much length from x equal to 0 to L it will travel. So it is very simple that it will have some L over V time scale, so that that particle will reach here. Now if we repeat this thing again and again, as this process is deterministic in nature, what you will find that the position over time you will find that same path again and again, and it will have that L over V time, that will be the mean time also. Now in this particular situation, if we introduce restart, that means what? If particle is here, if we restart it again to its initial position, then definitely that is going to delay the process. So that is going to delay the completion process. So if we have simple drift, deterministic drift, nothing else, and if we restart, what we will find that it will delay the process. Now we said that in a stochastic search process, it may actually sometimes accelerate. So what is the reason? So here we have not considered the thermal noise. So when the thermal noise is important, if we consider the role of the diffusion, so what will happen? So let us see a pure diffusion situation. So here particle is there, and suppose at L distance there is one absorbing boundary, and here it can go up to minus of infinity. So it can escape towards the very large value. Then what will happen? So every time if we start stochastically from here, so particle will follow some trajectory and sometimes it will reach, and depending upon that we will get some time and we will take mean and we will get the mean first passage time. Now what happened, as this left hand side boundary that is open towards minus infinity distance, so some of the trajectory particle will follow when it will go towards very large value of negative distance, and it will actually come back to plus L, that is the target, after infinitely long time. Therefore those trajectory, number of those trajectory will be less, but those trajectory will make this mean first passage time infinite. So in principle, if you consider mean time, it will take infinitely long time for completion of the process. Now in this particular case, if we do the restart, that means what we can do, so for all this trail, so what you can find that if we restart it here, that means we are giving that particular chance to find this target very quickly once again. Therefore we can truncate the effect of these long trajectories, so that we can get some benefit. And actually what it has been found that if we introduce restart here, so that makes the completion time finite. So now if we just formalize in terms of the calculation, so what we can find, so this observation was first reported by Evans and Satya, Martin and Satya in 2011, and what they find, if we do the calculation, you will find that indeed it is finite, and it has this particular type of expression, and there if we plot that mean first passage time with the restart rate, you will find it follows some minima. So this is we can consider as optimal restart rate, and one can find from this expression and from this minima also, you can find that this goes as d over L square. So this is basically the diffusion's time scale, you can see that. So what does it mean? So it means that if we have one boundary at L distance and other side it can go to infinity, so one particle starts to diffuse, so we allow it up to that time at which it may reach to that absorbing boundary. If it appears there, fine, process is over. If not, so then what is the probability? Either it is going there or in between there. So if not, you restart it there. So we will allow until that point that it diffuses that distance, otherwise is restart. At that particular point, if you restart, we will get the maximum benefit here. Otherwise what will happen in the both side, you can find that for r equal to very high, that means if we restart too frequently, definitely the completion process will be over, because those short trajectories now those will also be hampered. So it will make that mean first passage time longer. On the other hand, if we consider the resetting rate tending to 0, in that case that means we are not giving any restart. So no restart at all, that therefore the effect of those long trajectories are now very much more prominent. So that will increase the mean first passage time. So this is the beauty of this simple calculation and phenomena. So now as in our problem, we have drift and diffusion both, and we have two absorbing boundary. So before that, going to that, we want to see that what will be the effect of drift plus diffusion in presence of one boundary. So now coming back to that previous example, if we consider, so in deterministic situation, L over V was the time scale. Now for pure drift, pure diffusion, we see that when b equal to 0, restart can enhance the completion process or accelerate the completion process. On the other hand, if there is no diffusion, so then definitely it is going to delay it. Now if we introduce both, so what we did, we find one observable or a quantifier, we can say that, or parameter rather we can say, that gives the sense of both, that drift and diffusion. So the Peclet number, so this is basically the ratio of the rate of advective transport and diffusive transport. So if we consider the Peclet of the system and we do the same first passage problem in presence of both diffusion here, and if we introduce diff, and on top of that the restart. So restart is that we are restarting with a rate at x from any position, and we are keeping it back to its initial position here. So if you do that and you calculate the survival probability and do some appropriate calculation, so we get some modified expression of mean first passage time like that, where at v equal to 0, you can find that Martin-Evans result back with that particular minima. Now if we introduce some drift there towards the boundary, absorbing boundary, you can see that the minima position is going towards the very less value of restart rate. And after certain strength, you can find that the optimal restart rate is 0. What does it mean? So if drift is very strong, then because of the drift, particle is being absorbed automatically. If we give restart, that then we are hampering. That means there is no such optimal restart rate, or optimal restart rate is 0. So that situation arises. So now, so what we did, so we find here basically a signature of some sort of transition, that up to which strength of the drift restart will assist or not the completion process. So in terms of that Peclet number, as I mentioned, if we just plot the scaled optimal restart rate, this R start 0 is the optimal restart rate with v equal to 0, then what we will find, you can see when Peclet number is 1, exactly at 1, so until that point you can find that process can be expedited by restart, otherwise not. So we find some sort of resetting transition here, and we can analyze that this R star, how it goes. 1 second, yeah. So it will be kind of proportional to Peclet number with a negative sign. Okay, good. So now coming back to our deep diffusion making process. So what do we have? We have two things. One extra here. One is that two absorbing boundary, and we denote it as one right decision, another wrong decision. other thing is that this V can be in the both side now. So the common thing is that if we put cheese here, we can assume that this is a positive drift, and there might be also, we can also assume a negative drift under a situation. Suppose Tom is keeping some more cheese with him. So basically Tom is trying to trap Jerry, so keeping more cheese. In that case, Jerry will be deceived and he will try to run towards Tom, so that we can consider as a negative drift. So these two differences are there, and now if we set all this parameter here, so what are the parameter of interest? So we want to see what is the accuracy at which this particle will reach to the right decision. Another one, that what is the minimum common mean minimum time it requires to take any decision, right or wrong. So that is decision time, and over accuracy we denote it as reward ratio. And now we will try to optimize this reward ratio in presence of stochastic resetting. So I am coming back to our problem again. So before we go towards result, one more important thing about the stochastic resetting, we should explain that when does this restart helps in terms of completion time. So there is another analysis in terms of the coefficient of variation of the mean first passage time. So what does it mean? That whenever the long trajectories are prominent, mean first passage time was high, right? Now if we give restart, so we are truncating them. So basically what we are doing, we are trying to reduce the fluctuations of this first passage time. Therefore, and the second point is that if we have a particular strength of drift towards the absorbing boundary, then because of that influence of that drift, the fluctuation of first passage time will be less, right? So drift will control. So what Shlomi found in 2016, that if we find that this coefficient of variation, that is the fluctuation over mean, if it is greater than 1 without resetting, if it is greater than 1 without resetting, then what you will find that it will definitely help. If we introduce restart, that will definitely help the completion process. That means restart time will reduce. Otherwise, it will not. So taking this information in mind, what we did in our problem, we have not introduced restart. Without restart, we find that mean completion time or mean decision time to any of the boundary and its fluctuation, and as a function of both the drift and the initial position. And what we find that we can introduce this criteria, and we find that there is some very non-monotonic way. You will find some zone where restart doesn't help at all, and otherwise restart can help in reducing the decision time. So here you can see that this both V and X naught can influence that decision time if we, I mean the fluctuation of decision time and its ratio over mean. So this is the way we can identify the zone. On the other hand, in our decision making process, other important quantifier is the accuracy. That is the what is the probability of this particle to be escaped towards the positive or correct decision boundary. There also, if we choose one particular R, so this is R restart rate equal to 1, and if we find what is the gain in terms of accuracy and put this criteria, so what we find that what is the positive here. So there is some zone where you will find that restart will increase the accuracy. Of course, that is also function of R. Here we have plotted with a particular R. So therefore, from these two very plot, you can see that this problem is very non-trivial way they are connected, and if we want to calculate the accuracy over time, that means accuracy speed trade-off, so that we might get some fascinating result. So let us see what happened. So very quickly and briefly what we did actually, so we considered the underlying 1D Fokker-Planck process with the stochastic resetting. From there, if we can calculate flask, and if we go to the Laplace space, from that under appropriate condition, we can find out the splitting probability, from where we can find epsilon plus minus from the J plus minus, and we can find accuracy. Simple. Similarly, if we consider backward Fokker-Planck, and if we consider survival probability Q in presence of restart, from there under certain condition we can find the mean decision time also of this problem. Once we have these two, we calculated these two, and then we can find the ratio, and we try to optimize the same. So what are the expressions? So expressions are little bit clumsy, so we try to simplify it, but unfortunately we are not able to. So this will be the mean first phase time, mean decision time expression. This is the accuracy, and from this ratio we can get the accuracy over accuracy over time ratio. Fine. Now what are the result? So let us first consider a situation where both the asymmetry, the spatial asymmetry like x position of x naught and the direction of drift. So these are the two asymmetry which can split the probability from 50-50 to unequal probability, right? So they are aligned. So both of them are working towards taking more accurate decision or correct decision, you can see from here. So in that particular case, if we calculate mean decision time, we find that with stochastic restart, of course it will show a minima when that V value, the drift value is not very high, and when it is high, definitely from our previous observation, in this situation also what you will find, there is no minima and it will always increase only. So you can find some associated R star also. And for accuracy, what you find, doesn't matter whatever is the restart rate for a given parameter set, but you can find that if we introduce restart, it will increase the accuracy, and after a certain time it will go to the maximum saturation in presence of V, you can see that. So basically what we can say that the maximum, I mean most accurate, that means 100% accurate result you can reach quickly by introducing stronger restart rate. So these two, now if we combine and if we try to find the reward ratio RR, so we scale this reward ratio with reward ratio in absence of resetting, and what we find, you see that V equal to 0, that means pure diffusion situation, and this ratio you can find that when V is not very high, then always we can find it is greater than 1 for a particular restart rate, and in fact for a pure diffusion system with this decision making process, no drift, so the gain is maximum, gain in terms of reward ratio, that amplification of this reward ratio is maximum, and that is up to 300%, that means 3 times, which is pretty high. And if you have V, that means what? If we if already there is some spatial asymmetry towards correct decision, which actually Dr. Arnopal analyzed that, whatever the gain we can expect, that gain will be maximum. Now if we introduce some V towards that, we cannot reach to that gain. So that gain will be less and less, and when Peclet will be very high, what we will find that we are not getting any more gain in terms of reward ratio. Okay. So this is the key result. Now if we consider competitive drift and spatial bias, that means as I was mentioning, suppose the spatial bias is towards correct decision and you have this drift towards negative diffusion. So Tom, you can see here, Tom is sitting with some piles of cheeses. Therefore Jerry will be confused that okay, so this is the correct path I should go, like that. So in this particular situation, one interesting thing happens, and which we are still trying to analyze the time scale, that double turnover in terms of mean decision time one can observe. So this is what physically we understood, that this is because of the competition of the two time scale. One is arriving from this length over not length over V, because V is in this direction, this length and diffusion coefficient, and another is of course the strength of the V. So these two, so basically that length towards correct decision is less, so it is trying to be finished there. On the other hand, by the time the process is complete, there is some sort of decay process, just like in population dynamics, some death and birth process, so some sort of death process is there like that. So that is trying to forcing him towards the negative direction. Competition of these two time scale is giving us a double turnover here in terms of mean decision time, and we are still trying to understand the exact location of this minima and maxima. And in terms of the accuracy, we get almost similar type of result there. What we can say that when V is obviously, when V is very strongly negative, so it will take higher restart rate to reach the absolute accuracy, and that is physically obvious because V is negative means V is trying to push that particle to go towards the negative wrong decision. Now by giving restart we are stopping that probability of wrong decision, so more frequent restart will increase the probability of the correct decision or right decision. So now if we just take a turnover, so here two interesting results we find. First is in terms of the amount, so you find that here the gain is even, we can get maximum gain in terms of enhanced reward ratio even more, 400%. You can see here for particular V, and this you can see that starting from pure diffusion, if you increase that negative V up to a certain point of negative V, this enhancement will be there. After that again it will reduce. So you will find another turnover here, and that is also again obvious when that negative drift is too high. So in that particular case, what we can expect that decision time, the way we define the decision time is the particle unconditional mean first passage time. Particle will be absorbed by any one of this boundary. So that decision time was very low. Now if we incorporate restart there, decision time will increase, and accuracy has some range to be increased, right? So overall you will find that it will come down for very high value of V. So two non-monotonic behavior, one in this side, another in terms of V also you will find this non-monotonic behavior. So therefore overall what we can say that this is a charming or wonderful problem where you can identify under which condition the speed accuracy trade-off will be influenced or amplified more efficiently in presence of stochastic resetting, and we find that if there is no asymmetry in terms of spatial symmetry or drift, there is no use of resetting to increase that Sato problem. On the other hand, if there are asymmetry, then it can actually influence, and when the spatial asymmetry and drift they are working in opposite way, in that particular situation interestingly we can amplify it more efficiently. Now the open issue, and anybody interested, particularly Dr. Arnopal's group, they can collaborate. So as I mentioned in context, right, so we can now extend this idea to this discrete state system where the stochastic resetting will be, as the previous speaker was telling, so from any particular state there should be some policy, so like right hand side, left hand side jump and coming back to the free enzyme and substrate. So introducing some sort of appropriate policy here, and what is the role of this unbinding process if we explore. So I believe that will be a very interesting problem, and in terms of the physics of the problem we can forget everything about enzymatic kinetics and all. We can just consider a deuce situation in tennis. So where we find that from deuce player 1 can win first advantage and then player 1 can win, or from advantage it can come back to deuce again and second player can win successively winning 2 points, right. So here instead of one advantage, if we introduce suppose multiple advantage, advantage 1, advantage 2, advantage 3, and then one player can win, in that particular case from any nth advantage, if we put another option that from that advantage state particle can come back to that deuce directly by some particular like some AS or some point. So that will give us a very beautiful effect of stochastic resetting problem in this type of discrete process. So in general from deuce it is driftless, we can assume that drift equal to 0, but as we know that if it is French Open and Rafael Nadal in his best, then from deuce also, so there will be some bias towards Rafael Nadal. So in that way we can introduce some sort of drift there as well. So with this I would like to thank my collaborator actually from whom I am actually learning this stochastic resetting problem, of course Arnav and Shlomi and Somrita, both of them. Arnav and Somrita was visiting Shlomi's lab. That time I had an opportunity to visit his lab and for a couple of months, and from there we started, and of course my small group at IIT Tirupati, and thank you everybody.
Yeah, thank you for a nice talk. The floor is open for questions. There.
Yes.
Thank you. Very nice talk. For the stochastic resetting, you showed this how you modify the Fokker-Plan equation. right, where you had a negative and positive term. There was something like Q of t that you have introduced. So can you explain what that Q of t is there?
Oh, that is survival probability. Okay. So,
Okay.
Going back to that slide. Here, right?
Yeah, yeah.
So,
okay.
Q of t is that it can go to minus infinity.
Okay,
So, at time t minus infinity to this observing boundary, what is the total probability that particle survives?
Fine. So that means you, to actually model this stochastic resetting, you add these two terms. But then, as you know, this Fokker-Planck equation has to, the solution of this equation will satisfy Chapman-Kolmogorov equation, which is a Markov property. But then if you add these ad hoc terms, are you still maintaining detailed balance? Are you still retaining the Markov property? Have you tested that? Because to me, it looks like you're going to break the detailed balance by doing this. Is that a problem?
Yeah, so basically you can say that only this part is like coming from the pure Fokker-Planck equation.
Yes.
And this is like in the way in our master equation jump process, the way we add it. So it is like that. So these two term is purely out of equilibrium. So at any time t, stochastically with r rate, we are picking the particle from there and keeping it back to that initial position.
But you're not going to do reverse. You're not going to do ever the reverse.
No, yeah.
So that means you're breaking the daily balance.
Yes,
so
out
that
of
means
equilibrium. Yeah,
so
yeah.
No. Out of equilibrium is different from breaking a detailed balance. So
Yes, yeah. So we are breaking, in that sense, we are breaking the detailed balance. Yes.
that should be a problem, isn't it? I mean,
No, problem in terms of what you are saying?
because it's not a Markov property anymore. So so if you add these two terms, the solution of this, have you tested?
Yeah, so.
Yeah, doesn't it look kind of unphysical to do this then? I mean, because if you
were thinking about having a t is equal to 0 jump, in that sense you can say, but
maybe I'll talk to you later about this more. The other question I had, do we have time? Or
Yeah.
so just one more question. It's about the resetting. When you do resetting, especially with the drift, you also talked about drift towards the right direction and drift towards the wrong direction as well. Suppose if you are doing drift along the right direction, and let's say you have a reset rate that may be given by this diffusion time that you mentioned, right? Some optimal diffusion time. So is it important to actually do the resetting when you're already traveling in the right direction, or should you do only resetting when you're traveling in the wrong direction? Shouldn't that be involved in decision making?
Yeah, so that sense is coming is more pronounced when V is pretty high. That means Peclet is high. LV over 2D, that
Right.
advective transport
Right.
over diffusive transport. Advective transport is dominating over diffusive transport. That time definitely. So when that LV over 2 high, automatically it is being completed. So why to disturb that process?
Right.
So then it will, slow down the completion
Right.
process. That's why there will be one resetting transition I have shown
Okay.
there.
There are too many information.
yes,
Maybe I didn't process it.
ah,
That's
ah.
fine. Yeah.
So we have to consider here. So as you mentioned correctly, so this is the zone without resetting. So based on the drift and
Right.
the initial
This is-
bias, you
okay.
have some zone where only actually it will help. Otherwise, it is automatically going with a very confidently it is going towards the correct decision. Then why to disturb it?
Right. Okay.
Yes.
Thank you.
Yeah.
Yeah, maybe one last question before we break for coffee.
So when the drift is towards the right boundary, can you explain what is the physical reason why the accuracy epsilon plus monotonically increases with respect to resetting rate?
Yeah, so that you can say that as if drift is not very high, so on drift is very high, then it is already 100% accuracy. You can see that. So there is no effect of effect in terms of resetting on accuracy because it is 100%. It may happen now. If you give resetting, it will happen little later, but it will be 100%. But if drift is less, that point also, although it is towards accurate, suppose 80%, 20% like this, that time also there will be few trajectories which will try to go in the opposite direction, right?
Yeah.
So by giving a controlled resetting, we can actually truncate those and we can enhance or accelerate the possibility or exploring this character.
Yeah,
But this will be true only when drift is
yeah, when the drift is low, it is understandable, but when from the plot it seems for any values of the drift it increases monotonically. So when the drift is very high towards the right boundary, it seems so resetting will only delay the process.
Yeah, drift is very high, you see always it is 100%. Resetting will delay the process, you understand, but it will not hamper the accuracy. Suppose drift is very high, 100% it will go there, okay. Now if we do reset, it will delay that completion time, but whenever it will get chance, because of the strong drift, it will go that side only, okay. So that's the idea. So it will not reduce it. So accuracy will be governed by the strong direction of the drift, okay.
Okay, thanks.
Okay, so let's thank the speakers again. So we will drift towards coffee and then restart in 20 minutes.
Yeah, thank you.